Linear recurrence relations describe a wide range of problems, and their solutions are surprisingly elegant. Let us go through the properties contained within the name. The relations are linear, so all of the variables occur as just some multiple, with no exponents, products, or other manipulations. Recurrence describes how the variables all describe one sequence, which develops its values in a recurrent way through the aforementioned linear addition of prior values. The most famous example of a linear recurrence relation is the Fibonacci sequence. Starting with 1, 1, 2, 3, and 5, the sequence repeatedly adds up the previous two terms to get the next. We could express this relation with the equation where f sub n plus 2 is equal to f sub n plus 1 plus f sub n. Importantly, we must include the initial conditions for the series in order to get the full picture. Though the equation describes how the elements relate to each other, the initial condition helps set the starting point. If we change the initial conditions, we would create a completely different sequence. For instance, starting with 1 and 3 instead would lead to the sequence 1, 3, 4, 7, and 11. These linear recurrence relations have lots of applications, so let's list a few. They can be used, obviously, for gaining greater insights into sequences like the Fibonacci one, solving them for a closed form. They can also be used to model random walks, like calculating how long it would take for a particle of gas moving randomly in a room to reach one of the ends. Since a measurement at any one position is slightly larger than the average of the measurements of the outcomes at the adjacent ones, we can make a solvable linear recurrence relation. From a more educational perspective, they can be used as a way to introduce some concepts from solving simple differential equations, since it uses quite a similar approach, but with less complicated mathematics. Often, when linear recurrence relations are introduced, the solution is first given and then justified by showing that it just works. However, I want to try to approach how one might find the solution before using it. Consider the Fibonacci sequence and what happens as we get bigger and bigger terms. Our additions get closer and closer to reaching a pattern where the ratio of the terms approaches a specific value. It's fairly well known that this is the golden ratio. We can find it by assuming that the elements follow an arbitrary ratio perfectly. Let x be some random term, and let r be the ratio. Then, the next term would be r times x, and r squared times x. Using the relation for the Fibonacci series, we can solve the quadratic for r, to reach the golden ratio and another related solution. This example gives us some intuition for linear recurrence relations, showing how they are connected to multiplying by some ratio each time. This leaves us with two missing pieces. How would we fix the imperfection within the ratio, since the sequence never actually reaches it? And why do we have a second solution here, if only one of them shows itself through the ratios? Let's ignore the initial conditions for now, and consider an arbitrary relation with three terms. In an ideal world, this equation would describe a series with a perfect repeating ratio. We could represent the nth element with a times lambda to the power of n, where a is any initial constant, and lambda is the ratio we multiply by each time. Plugging these into the linear recurrence relation, we get this. Solving the equation for lambda, we will get two answers. For an equation describing a Fibonacci-like relationship, these solutions are the aforementioned golden ratio and its cousin. Using these values of lambda, we can get two distinct solutions by putting back the initial constants. If we try to combine these solutions by adding them together, it's easy to see that it will still work. The equation is quickly split into two halves, one for each of the ratios, each of which works on its own. So now we have this compound solution consisting of two ratios, each of which has a constant that can manipulate the value. By manipulating these constants, we can change what the values of the first few elements are in this ideal ratio-based sequence. In fact, we can set the elements to exactly what the initial conditions would tell us to. In this way, we discover that with the proper coefficients, this solution is actually exactly what we were looking for earlier. It is a closed, non-recursive form that describes the elements of the sequence. It answers both of our questions at the same time, solving the inconsistencies with just one ratio by adding the second number we didn't know how to use. This method, replacing the sequences with a power sum ratio and then adding them together with coefficients, can be extended to more complicated equations. Linear recurrence relations with more terms would need more initial conditions, but they would also result in cubic or higher order equations that would lead to more ratios with more coefficients, which can be adjusted to fit whatever initial conditions we desire. The initial conditions don't even have to be the first few terms, as it is usually described, but can come from anywhere, like taking the first and last term in a sequence. However, there is more to the story for linear recurrence relations. The method so far encounters problems when one or more of the roots of the equation we get repeats, since then there won't be enough coefficients to properly account for the initial conditions. The method is also limited to when there are no constant terms within the relation, since trying to add that without changing anything in the above solution would cause problems when doing the additions. Unfortunately, those topics will have to wait for another time. Hopefully, that introduction to linear recurrence relations not only shows what the solutions are, but explains how one might come about discovering them.